Welcome to the engineering measurements class. So last class we have discussed about aggregates, how to find it out the specific gravity and water absorption of aggregate. So in this class we'll be discussing one more experiment on aggregate, that is the sieve analysis of coarse aggregate. So if you recall, we have started our this course, this lab experiment for civil. We listed total 10 experiments, out of which 6 will be the basically physical experiments, and remaining 4 will be MATLAB based experiments. So experiment 1 we discussed about the shape test, because aggregates we are studying in details. Aggregate is one of the main ingredient of the construction industry. So if you do any construction, we use aggregate extensively. So before using aggregate, we have to understand its properties. So that's what we started understanding the aggregate properties. We discussed about the shape test, and then in the last class we discussed about the specific gravity of aggregate and water absorption of aggregate. So in this class we'll be discussing about the sieve analysis and sieve analysis of this. Just excuse me, this is not coarse, this is coarse. Coarse means a bigger size, coarse aggregate. Okay, so which is large dimension in nature. So these are the aggregates basically you will find in a field, in a construction site. So how the aggregates are actually produced? Aggregates are basically igneous rocks will be there on a site. From a hillside they cut the big pieces of stones, and then using this type of crushing machine will be there in the site. Using this crushing machine, basically these big small pieces of stones will be disintegrated into small stones, small chips like that. This we call it basically aggregate, and this is specifically coarse aggregate. Even sand also we use for the construction purpose. So sand is also a type of aggregate that we call it fine aggregate, which is fine in nature. And this aggregate is a coarse aggregate, means large in dimension. So aggregate more than 4.75 mm diameter, we call it is a coarse aggregate, and aggregate less than 4.75 mm diameter, we call it is a fine aggregate. Okay, so these are actually the coarse aggregate. Today we'll be discussing about the sieve analysis of coarse aggregate, which is dimension is more than 4.75 mm. So now, so if you see in a site, this type of crushing machines are available. In this crushing machine, basically these big stones are kept, and it is broken into small parts. Okay, so now if you see in this portion, so for some construction purpose we need 20 mm diameter of size, or some in some construction we need 10 mm diameter, in some construction we need 6 mm diameter chips, like depending on the use. Like if you see in the railway lines where the ballast we keep besides the railway track, that diameter of that dimension of that aggregate is quite large, right? 20 mm, 30 mm we use. Even for the road construction also, when we make our subgrade soil, that time we use bigger dimensions of aggregate, right? But when we construct the slabs, or the beams, columns, that time we use that lesser dimension, maybe 20 mm diameter or 12 mm diameter size of aggregates, right? So while crushing the aggregate, we have to get proper size of aggregate, because which is required in our construction purpose, that only we should make, right? So on a site, when we have the aggregate, it will be mixture of all different types of aggregates. You cannot get all aggregates are of 20 mm diameter, or all aggregates of 12 mm diameter, because it is prepared in a crushing test machine. So in the crushing test machine, basically all the different types of grades, sizes of aggregate will come out. So in that sense, if you need 20 mm, so you may not find all aggregates will have exactly 20 mm diameter. Some will be 25, or some will be 16, 15, 10 also you will find. So in this experiment, we'll find it out a particular grade of concrete, how we can call it. It is a 20 mm aggregate, or it is a 16 mm aggregate, or it is a 10 mm aggregate. How actually we can classify the aggregate, because in reality aggregate you will find even in 20 mm grade of concrete aggregate also, we will find some will be smaller dimensions. So that's what we'll do it. We'll perform a sieve analysis, and we will find it out what is the grade of what is the dimension of the particular grade of aggregates. So the apparatus required for this experiment will be we will be using simple balance and the sieve sets, and then the aggregates. So sieve sets will be using 20 mm, starting with 20 mm. At the top will be 20 mm, then we'll use the 12.5 mm, then 10 mm, then 6.3 and 4.0, like that. We'll stack all the sieves, and then we'll perform our experiment. So the this is the table. Basically, once you perform the experiments, you will find this type of table will be available. So in that, basically, again we are finding out which type of aggregate has actually passed through each sieve. So basically, we'll put all 1 kg of aggregate, we'll take from the sample 1 kg of aggregate, we'll measure this using the balance, and we'll keep all the samples into the top sieve. So top sieve is 20 mm, then 12.5 mm, 10 mm, 46.73 mm, like that. We'll one by one we keep our sieves, and then 1 kg of sample we'll take it and we'll keep it at the top means 20 mm sieve, and then we'll do the shaking, that is sieve and sieve shaking will do it. So then all the smaller dimension aggregates will be passing through the each sieves. So some sieve, some particle will be there at the top, means the dimension is more than 20 mm, that will be retained at the 20 mm sieve. Now some will be at the 16 mm level, because those two dimension in between 20 to 16 mm, that will be retained in the 20 mm sieve. Like that, all sieves will find the aggregates are retaining. Now 1 kg is total we have taken, and each portion we are taking, we are few samples will be reduced. So now we'll collect it from each sieve how much is retained, and we'll measure it out, and then we'll make a table like in each sieve how much is passing. Okay, so based on how much is passing in and how much retain in each sieve, then we can conclude that which sieve, I mean which type of aggregate that is. So this table you will find it out in the IS Indian Standard 383 1970. So in that year, this IS code has written. So in that IS code you will find it out. For example, if you are and if you tell the 20 mm grade of aggregate means these are the criteria should be. So in a 20 mm grade of aggregate, all that 85 to 100% should retain in the 20 mm sieve, but 40 mm sieve all should passing. So like that, the criteria they have given. So if we'll find it out, we'll do the experiment, and then we'll check with our values with this table which one is matching, and that will be corresponding to the size of the aggregate. So for example, if the 63 mm, that is a very large dimension of aggregate, if you take, in that case all aggregate should pass through 80 mm sieve. Okay, but in 63 mm sieve 85% should retain. Then in 40 mm sieve, 0 to 30%, if it is retaining in 40 mm sieve, then also we'll consider it as a 63 mm diameter of aggregate. So that is the experiment we'll be performing in the lab, and then we'll be tabulating our values, and we'll match it with which category our current sample is matching, and that will be corresponding to the final grade or final dimension of the concrete aggregate. Now let's go to civil engineering lab and let's perform. So now we are into civil engineering lab. So for this experiment, we need aggregate sample, we need balance, and the sieve set. So again, sieve sets are kept in a sequential manner at the top 20, 16 mm, then 12.5 mm, 10 mm, 6.3 mm, and at the bottom we have the pen. So this is the total apparatus required to perform this experiment. So now we will take the 1 kg of sample, aggregate sample, in a balance, and we'll find it out. So here you can see we are collecting the exactly 1 kg of aggregate sample from the total aggregate. So now it is exactly 1 kg of aggregate that we are keeping it into the top of the sieve. So this entire aggregate will be sieved, and then the smaller particle will be retained in each sieve, and the smaller particle will be passing in each sieve, and the larger particle will be passing from one sieve to another sieve. So we just keep close on the top of the sieve, and the base we have the pen. So if you see, all the sieves are placed in a sequential manner. So at the top we have the Coarse grade, that is 20 mm diameter, and then we have 12.5 mm diameter, then we have 16 mm diameter, 10 mm diameter, then 6.3 mm. So total, these are the different grades, different size shapes we are keeping one by one. Then properly we have to shake it so that all the particles should pass through the respective sieves. So now you can see all the sieves, how much aggregate is passing in each sieve from 20 to at the end at the pen. So all the sieves, now we will take one by one measurement and find it out in each sieve how much aggregate has retained. So now you can see, will be one by one we'll be doing the finding out the how much aggregate is retained in each sieve. So now we set the uh, balance to 0. That is, make sure that every time when we take any balance, initial reading should be 0. Then all the one by one we are keeping the samples and finding out how much is the weight passed through that sheet and the value that recorded in a table. So this one is the larger one, that is the 20 mm. See how much it is retained, that is recorded in the balance, and we are putting it in the observation book. So this first sieve is over. Now next, like that, one by one, all sieves will be taking out how much aggregate is retained in each sieve. That basically we are finding out and we are recording in our observation sheet. So this is our second one, that is a 12.5 mm sieve. Make sure that all the samples you are collecting from the sieves, and then you are finding out how much is the total aggregate record retained in the sieve. So the second sieve is over. Now we will take the third sieve, that is 10 mm sieve. This is the 10 mm sieve. So like that, all the sieves we have to find it out how much total aggregate has retained. All the values will be recorded in a table. So after the experiment, we just captured all the recordings, whatever we have done. So all the sieve records are there. How much aggregate is retained in the each sieve are here tabulated below. So in this table total, we have taken total 1 kg of sample. So in that 1 kg of sample, basically the 20 mm to 16 mm. So different sieves we kept it. The top was 20 mm, 16 mm, 12.5 mm, 10 mm, 6.3 mm, and at the bottom you have the pen. So there is a total sieve assembly we kept it. Then at the 20 total 248 gram total aggregate is retained there. Then in the 16 250 gram aggregate is retained. Same 12.5 156 gram aggregate has retained. 10 100 gram, 6.3 170 gram, and in the pan at the bottom also 53 gram, that is dust particle and small aggregates are actually retained. So if you add it all, you will get a total of 1000 gram of total sample. So like that, basically when you perform the real experiments, real life, then at least we have to take the three measurements. So this is one measurement, then with another samples, in the same bucket, same another grade of sample, we'll take it, and then we'll do it second measurements, and then we'll have third. So we'll take all these threes average, and then we'll find it out our final value. So here you can see that these are the average values we got it. So here only single experiments we have performed, so we just place the same value, but in real life we have to minimum perform the 3 experiments. So now this column is basically percentage of total weight retained. So in each sieve, how much aggregate is retained. So the first is 248 gram has retained, right? So the percentage weight retained is total was 1 kg, that is 1000 gram. So 248 divided by 1000 into 100, which will give you 24.8 gram of sample retained at the 20 sieve. Similarly, at the 16 sieve, 250 gram, which is nothing but 25% of the total aggregate is retained. So like that, all the values we are keeping it in this column. So next in this column, that is cumulative percentage of total weight retained. So this is cumulative. Cumulative means total how much retained in the 20 total how much retained all above the 16 So like that, cumulative basically we are finding out. So this is nothing but 20 is the first one, so all that is 24.8 same. But at the 16 sieve, basically it will be cumulative, means 20 it retained 24.8% and in that 16 it retained 25. So we have to add these both, and then that is the total percentage of aggregate retained at the top level, I mean at the 16 level. Similarly, for the 12.5 sieve, if you see, the total cumulative retain will be 49.8 plus 15.6, so total it comes out to be 65.4. so like that we have to find it out the cumulative one. So this one will be 75.4, will be 65.4 plus 10, which is nothing but 75.4. so like that we have to find it out the cumulative retained, how much cumulative retained in each sieve. So at the last, basically all are actually retained, right? This is 100%. And this percentage, this column is basically percentage passing of each sieve. So if you see at the first 20 sieve, only 24.8% retained, right, at the top sieve. But how much is passing then? The remaining 75.2% is actually passing. Like that, similarly 16.6, 16 sieve, total 49 is cumulatively retained. Then how much is passing then? Passing is 50.2, right? This 100 minus this column basically will give you this column. So now we got it in each slab or each sieve, basically how much is passing. So once we get this chart, this is how much is passing. So now based on this value, basically we can classify the aggregate under in which category, either it is 20 sieve or 20 aggregate, or it is 16 or 15 whatever it may be. So once we get this type of tables, then we'll use this chart as I shown you earlier, that is IS 383. You will get this chart. So here you will see different categories of aggregates are there. So for 16 almost 85 to 100% should retain at the 16 whereas at 10 0 to 30% will be retaining. So like the 12.5 aggregate, single grain aggregate, it will have 100% should retain at the 16 So but in our case, our aggregate is in this range, so 20 range, actually 20 and 16 also, both in middle basically. So our aggregate is basically in middle, so 15 or 16 to 20, maybe 18 mean diameter you can consider. So like that, basically we have to perform the experiment in lab, and then we have to interpret the result using this chart. So this chart is available in Indian standard 383. So in that code, basically we'll get this table. So like that, in any sample, basically we have to trial 3 times. 3 times we have to repeat the experiment, and then we'll find out what is the average value, and that will match it with which column it is matching, and corresponding to that, that will be the nominal size of the aggregate, for that will be used for the construction purpose. So in this experiment, basically we have learned how to find it out, the nominal diameter of aggregate using the simple sieve analysis. So this method is only useful when the aggregate is coarse aggregate, means the nominal diameter of the aggregate is more than 4.75 mm diameter, then we can perform this experiment. So in the next class we'll be starting our new experiment, that is on surveying. So basically in aggregate we completed 3 experiments. First one was aggregate shape test, next we performed aggregate water absorption and specific gravity test, and in this class we performed the finding out the nominal diameter of the aggregate. So in the next class onwards, next 3 experiments will be surveying experiments that will be discussed in the next class. Thank you.